Hello and welcome. My name is Tyler Marks and I work in Michael Gord's lab at UCSB. The title of this project is Stimulus-Dependent Representational Drift in Primary Visual Cortex. So it has to do with the long-term stability of single neuron stimulus representations in visual cortex. Almost every chronic recording study that's been performed in visual cortex demonstrates a very high degree of stability with respect to single neuron stimulus response properties like orientation tuning, spatial frequency tuning, and size tuning. So it would appear that neurons that are selective to some stimulus feature are very unlikely to change the way that they respond across many days or weeks. However, almost all of these studies utilize a version of an oriented grading stimulus, a very simple artificial visual stimulus. Very rarely has anyone looked at more ethological, naturalistic stimuli in this context. And so it's possible that our perception so far of single neuron stability in visual cortex is a bit biased. So what we aim to do with this study is to offer a direct comparison of the stability of neural responses to an artificial stimulus versus that of a naturalistic stimulus in the same populations of neurons. To do this, we use chronic two-photon calcium imaging in awake mice that are passively viewing both a periodic drifting grading stimulus, as well as a continuous 30-second natural movie clip. And we find that while responses to the gradings are highly stable, as expected, where the vast majority of cases neurons retain their tuning preferences over time, responses to the movies were often quite unstable, wherein they appear to drift from week to week. And if we evaluate even the subset of neurons that are responsive to both of the stimuli, we find that this representational drift is present to a much greater extent in the natural movies compared to the gradings. This is quantified by the representational drift index, which shows differential stability between the two stimuli that grows on average over time. And so this suggests that it's probably incorrect to think of stability as an intrinsic property of a given neuron, as we get different results based on the stimulus that we use. When we further characterized this drift, we found that it was present at the level of individual visual response events, where natural movie events were more likely to change over time than grading events were. We also found a relationship in which stronger events tended to be more stable than weaker events, although natural movie events overall were less stable than gradings events, regardless of event response strength. We also found representational drift in natural movie responses across cortical layers 2 to 5. To explore this, we use these small glass prisms implanted directly beneath our cortical window, which allowed us to image from neurons across multiple layers at the same time. And we also repeated these experiments for inhibitory neuron populations and found a similar degree of differential stability between the two stimuli as we did for the excitatory neurons. Lastly, we find that the between neuron correlation structure for the natural movies diverges from what it was at a greater pace than it does for the gradings. And so this allows us to speculate about how the differential drift that we see is related to between neuron connectivity, and that the early development of orientation tuning in animals may establish these strongly connected subnetworks of co-tuned neurons, which is a feature that might not exist for more complex stimuli, and which could account for the differential stability we observe. And if this is the case, then it demonstrates that certain co-tuned subnetworks of neurons can preserve more fundamental stimulus features while allowing for more flexible responses to complex naturalistic stimuli.